to 1 derivatives by the product rule. So probably at some point earlier on, okay, when you start off in calculus, you're going to run into this product rule. And what it talks about is the idea when you have two functions which are basically multiplied together. So for instance, here is a function which is h of x, and it has two functions, 3x squared, and then it's multiplying another function which is x to the 5. So when we have this, okay, this is a product of two functions. And now our main goal is to try to figure out what would be the actual derivative for this. Now, if you recall, when you were studying, for example, the summation of two functions or the difference of two functions, so I can point the link up above there to that, then you have found that if we did have two functions, so let's say fx, and then we were adding it to another function, so gx, okay, so if we had something like this, and you wanted to take the derivative of this when it is being additive, or, okay, if there's a difference, so meaning that there's a subtraction, all you did was you simply said, okay, well, we can take the derivative of the first function, and then we can add or subtract, depending if it's a sum or a difference, the derivative of the second function. So that was the rule for summation and the difference. Now, would we want to be able to have something very similar? Yes. Now, unfortunately, it's not that easy, meaning that I can't just say if this is, let's say, my first function right here, so this will be fx, and then it is multiplying my second function, okay, so this, let's say this is gx right here. Unfortunately, okay, the actual derivative itself, so if you wanted to find the derivative, it is not just, take the derivative of the first function and then multiply it by the derivative of the second function. So that's not going to work. So for instance, if we wanted to do that here, it's not very difficult because, we have two functions which really are just power functions, right, with a constant in front. So if I wanted to follow this rule right here, which I'll show you it doesn't really work, is that I would just simply take 3x squared, and then the derivative of that is 6x. And then if I wanted to take the derivative of this, let's say if this was my g of x, then this is nothing else but simply 5x to the 4. And then if we simplify 6 times 5, so that's 30, and then the x, okay, and the x to the 4, so that would have been this. So if it was this easy, right, if we would just simply be taking the derivatives of each functions separately and just multiplying, then that would be amazing. Unfortunately, it doesn't work. Now, how do I know that this isn't the answer? Well, because I can simplify this, right? So these two particular functions, if you take them, I can very easily just multiply. So I would get 3, and then I'm going to get x to the 7, right? That is really what h of x is. So I would have h of x is equal to this. And we know, again, because this is just simply just a power function, okay, with this constant in front, then the derivative of this is actually, 3 times 7, which would have been 21, and then this is x to the 6, which clearly these two are not equal. But this indeed is our derivative by simply using the power, okay, idea behind the derivatives. So if it's not this easy, then how could I possibly find the derivative when I have two functions that are multiplying each other? In this case, sure, I can simplify it. I can go all the way over here. It doesn't seem very difficult. But the functions are not always, this nice. So there are functions which possibly are multiplying each other, and they're not just power functions. They could be really ugly. So they could be something like this, which we want to be able to take the derivative of or simply differentiate. Okay, so if we use that terminology. So notice that in here we have, one function right here, and then we have another function right here. Now, do we really want to be able to, expand this entire thing? We could, but it would take us quite a bit of time, right? Or, what if we run into something like this, which is the last one, this h of u, and we wanted to differentiate that? Well, that now becomes a little hairy to try to keep expanding, okay, and then trying to figure out what the derivatives are. So we do want to know this product rule, and it turns out that the product rule, okay, in calculus is the following. So if you do have a function, so some function h, and it is basically the product of two functions, f and g. Now, we are making the assumption that both f and g, okay, so these derivatives actually exist, so meaning that the two functions, we call that they're differentiable functions, right, wherever we want it on the domain of interest. So if that is the case, then it turns out that it's not as easy as this, where you can just simply multiply their derivatives, because that certainly didn't work for us on that example. But it is not actually that difficult. So what it is the summation of, notice, you take your first function, you take its derivative, and you multiply it by the second function. So we don't multiply it by the derivative, we just simply multiply it by the function g. And then you add it, okay? So there's a summation where you keep your first function just constant, so it's just the same. And then you take the derivative of the second function. And when you add these two terms together, so when you're adding this term and you're adding this term, it turns out that it is actually the derivative of this particular function. And that is called the product rule, okay, for this derivative, okay, where you have f and then it's multiplying by another function g. Now, of course, the functions can be anything. So let's test it out, okay? So if we would go back in here and try to see what we would actually get. So if I came back in here and this was 3x squared and x to the 5, so 3x squared and then x to the 5, by the product rule, so if this was my f and this was my g, I'm going to just drop the x there for a moment, then the product rule would tell us that the derivative, okay, of our function would be equal to the derivative, okay, of the first function multiplied by g plus, we keep our first function constant, and then we take the derivative of the g. Okay, so if this is my f and my g, then this would be, so this right here is nothing else but simply 6x, and then I multiply it by x to the 5, plus, now I keep my first f the same, so 3x squared, and then I take the derivative of the second one, and this would have been simply 5x to the 4. And that is my entire derivative. Now you might say, well, that doesn't look like that. That is true because we haven't simplified it. So within here, so this first term, notice this is just 6x to the 6 plus my second term, so 3 times the 5 is 15. And then again, this is 6 squared. And these are just like terms. And notice what happens. This is just 21x to the 6, which indeed is that. Now, this product rule for this case, because these two functions are just power functions, we probably didn't need the product rule at all. We could have just done exactly what we did right here. We could have just simplified and then found it directly. It's a little bit less work. But as I mentioned, not all functions are that nice. So let's try to apply this product rule to some uglier functions. Now, if you're interested why this rule comes about and you want to know what the proof of it is, and again, anyone who's going into mathematics or engineering, computer science, or just you're very keen on knowing and not just taking things for granted, okay, I have done the proof for this product rule. I'll put up a link up above there. I don't want to make this video longer than it already will be, okay, because I'm doing, you know, several examples. So you can check that proof out, okay, on that link that I pointed out. So now let's try to apply this to, you know, these, which are not all very pretty. So let's take our first one over here. So I'm going to copy this, and I'm going to use the product rule to try to find out what the derivative would be. Now, both of these, so this function, okay, this is just a polynomial. This function is also a polynomial. So these are very well-behaved functions, okay? So they're differentiable everywhere. So we can use the product rule. So what I will do is, again, I will take the derivative, okay, of the first. So in this case, this would have been just negative 3x squared. That plus 1 is gone. This one stays the same, so it's going to be multiplying. So this is 3 minus x squared plus x cubed. So that's my first term, okay? So that's this term. And now I do the same. So now I will take plus. I will keep the first function the same, so this factor. And now I will differentiate this one. Now, differentiating this would be negative 2x plus 3x squared. And that is now my full derivative, okay, of the entire thing. So, if you want to simplify the whole thing, and your teachers ask you for that, sure, if they want to be that mean, okay, I'm going to just leave this because I want to be able to just show you that this is exactly how we apply the product rule. So you take the derivative of the first factor, you multiply it by the second factor, and then you add, you take the actual first factor, you leave it alone, so it stays the same, and then you take the derivative of the second. And you're done. So as hard as it might seem, okay, it's not actually difficult to apply this product rule. And, you know, so there are numerous ways, and please don't get fixated, as I see a lot of students do, that they think, you know, every variable is x. That's certainly not the case, because we apply mathematics to, you know, real life problems. And it's not all x, okay, in terms of variables. X just turns out to be a variable where we don't know what the quantity is. But for instance, you might have something like this, where maybe d, instead of our function f, d actually represents maybe some distance. And this is the distance with respect to time, okay, so as time goes on. And maybe that's the function that we have. So now, finding the derivative of this, so if I wanted to find the derivative, it's not very difficult. Take the derivative of this, it's simply 4, right? The negative 11 is gone. Okay, so that is 4, and then it would have been multiplied by 2 squared minus 1, plus, now I have to leave this first factor alone, and then take the derivative of the second, so that's just 2t, and I am finished, and I've applied the product rule. Now this is with respect to t. How about the last one? Okay, so this one seems pretty complicated, the way that it has been written out for us. So I'm going to copy this. And it has multiple things here. So notice that what it has is not only will we be using the product rule, but we will be using the rule of the difference. So in this case, we have a difference between two things. So this one will be annoying because we have to take the derivative now first of this. Okay, so whatever that derivative is. Okay, and then we have to take the derivative of all of this, right? And for both of these, we can use the product rule to do it. So for the first one, so let's call this one the first one. So the derivative of that is simply 2u. So I'm taking the derivative with respect to u there. Multiply it by negative u cubed plus u. And then that's going to be plus because I'm using the product rule. So u squared. And then in brackets, negative 3u squared plus 1. So there you have it. So that's that first one. And then the second one, so this would be my second. I have to use now the product rule between these two factors. So that would have been 2. So that would be, so first it's just 3. So that's the derivative of that 3u plus 2. Multiplied by square root of u plus 2u. plus, now I have to leave this 3u plus 2 alone. And now for the second one, okay, so this one, I'm going to just write it up above here. Okay, so this is the same thing as u to the 1/2 plus 2u. So that shouldn't surprise you. So that means that this is going to be 1/2, okay, u to the negative 1/2 plus just the 2, okay, because if I take the derivative of that. And now, we are subtracting these. So if I wanted to write it all out in full, this would have been 1, simply minus the 2, and that's the entire derivative. And sure, you can massage it, you can bring these inside of the brackets if you like. You can find the like terms, okay, and so on and so on. Okay, so that is up to you. Okay, so that is the application of the product rule, which is pretty neat. We can find the derivative of extremely complicated set of functions in here. Now, still be mindful, of course, so that, all of the ones that we did are pretty well behaved. But this last one that we did, we do have to be careful because we have the square root of u. So it's actually not defined for all u, right? So u can't be negative, okay? So for us, so we have to be careful there in terms of that function, okay? So in terms of the derivatives, you're going to be running into that problem as well because, you have the derivative over here. And this, of course, is just nothing else but simply 1 over 2, square root of u. So we can't have, u has to be, I guess, greater, okay, than 0 because it can't be 0 because we would have it undefined. So there is no derivative that exists there. And it has to be greater than 0 because we can't have negative values under the square root. So those are things that I like to point out to students. When I was doing this work, I never thought about okay, I just memorized these product rules and the summation and difference rules, and it was all okay, right? But the reality is, please be still mindful as a student to know that what's the domain here of these derivatives, right? Just so that we know where it actually exists. But applying the product rule, hopefully you will have found this video useful, that it gave you some kind of examples how it is applied. And now, you're pretty much far along in terms of calculus and applying these different rules for finding derivatives. Thanks for watching. We'll see you in a future video. Bye, everybody.